Previously, using the mechanical system analogy, we derived the general second-order differential equation that describes the position of this mass spring damper system as a function of time after the mass is released from some non-zero position. And we found that it's a second-order differential equation because we have two energy storage mechanisms, the mass and the spring, and we have no external force being added into the system, so it's a homogeneous second-order differential equation. And to completely solve this system, we need to know both the initial position as well as the initial velocity at time equals 0. Now we're going to look at the different models that we can establish with a second-order system. We have to look at some terms for our general second-order equation model. All right, so eventually we're going to be looking at how this equation model relates back to electrical systems and thermal systems. So let's take a look at these leading coefficient terms in front of the derivative terms. In our mechanical system, this was the mass of the system, but in general, we're going to call this the inertia of the system. All right, so that coefficient is termed the inertia. The damping, or sorry, the C, which was related to the friction, the viscous friction of the mechanical system, is in general called the damping, or the damping coefficient of the second-order system. And finally, this K, which is the spring constant in the mechanical system, is called the stiffness of the second-order system. Okay, so that's how we're going to generalize this model, the second-order equation model, to non-mechanical systems. Now we also have to be aware that there's a second form of the second-order dynamic system model, and that second form looks something like this. All right, it's d squared dt squared, so the second-order derivative of the variable that we're interested in, plus, now we're going to introduce some new variables, 2 times zeta times omega n times the first-order derivative plus omega sub n squared times the zeroth order derivative. Okay, so this is yet another homogeneous second-order differential equation, and it's related back to this second-order model right here, where we've introduced these two new variables, and these new variables are termed, where our zeta is termed the damping ratio, and omega sub n is defined as being the undamped natural frequency. Okay. By the way, the damping ratio, even though it's written as a zeta, and you can see each time I write this, I write it differently. And I had a professor in graduate school who would, instead of calling this zeta or the damping ratio, would write it as squiggle, or would call it squiggle all the time. So sometimes you'll hear me call this squiggle. But squiggle, zeta, and the damping ratio are all the same thing. Now the question is, how does the damping ratio and the undamped natural frequency relate back to these inertia terms, the damping term, and the stiffness term in our general second-order model? Well, what I'm going to do is I'm going to take a look at these two different models and then see if we can draw parallels between this model and this model right here. So the second model that involves the damping ratio and the undamped natural frequency I see has no leading term in front of the second-order derivative. So what I'm going to do is I'm going to take the the inertia, damping, and stiffness model, and I'm going to divide through by the inertia term. So if I do that, I wind up with the second-order derivative with respect to time plus c over m, which is the damping divided by the inertia, times the first-order derivative with respect to time, plus the stiffness over the mass, or over the inertia, times the zeroth order derivative, is equal to 0. Okay. And from this, now I can compare these two directly. comparing these two models directly, I see first off that k over m must be the same thing as the undamped natural frequency squared. So from this I have ascertained that the undamped natural frequency squared is equal to k over m, which means that the definition of the undamped natural frequency is the square root of k over m. Right, so that's the definition of the undamped natural frequency. Now we have to do a little more work to determine what the damping ratio is, or how that's related back to the inertia, the damping, and the stiffness term. To do that, I see that c over m, or the damping divided by the inertia, must be equal to 2 times the damping ratio times the natural frequency. Alright, so when I do that, I'm going to rewrite that as 2 squiggle omega n is equal to c over m. I also know that the natural frequency, since I've determined it before, is equal to the square root of k over m. So I'm going to go ahead and substitute that in. So I have 2 times the damping ratio times the square root of k over m must be equal to c over m. Alright, now doing a little bit more algebra to solve for squiggle, or solve for our damping ratio, I'm going to now multiply both sides by 1/2 and also by the square root of m over k. So my damping ratio is going to be equal to 1/2 times the square root of m over k times c over m. And doing a little bit of simplifying here, I see that this is going to wind up being c, which is the damping, divided by 2 times the square root of k times m. And that is the definition of the damping ratio. So if we can derive a second order model that looks like this, that has a leading coefficient in front of the second order, first order, and 0th order derivative terms, then we can also calculate the damping ratio and the undamped natural frequency using these relationships right here. And these are going to become important when we're looking at how to solve the differential equation that describes the dynamic behavior of a second order system.